Hello, everyone, and welcome to the Engineering Roundtable. I'm Jim Anderton, Multimedia Content Director here at engineering.com. You know, the process of engineering design is undergoing a sea change unlike anything seen since the advent of widespread computer-aided design 40 years ago. Now, CAD made rendering digital, but it didn't fundamentally change the way in which engineers and designers dreamed, developed, and drew parts and assemblies. And today that's changing. Cloud-based systems allow design software to operate with distributed, fast, and sophisticated hardware beyond anything found on a designer's desk or server room. And that same connectivity allows those designers to collaborate in ways that would be impossible with a conventional design review or engineering meeting. And now the software itself is taking on some of the design tasks. It's a dramatic future, and joining me to discuss the implications are Tim Greenwood, Senior Solution Architect Manager at Dassault Systèmes, Daniel Pizak, CATIA Mechanical Technical Director, and Kevin O'Donovan, Technology Evangelist. There's just so much to talk about. I'm going to dive right in. It's such a provocative and exciting subject. Can we kick off, perhaps with you, Tim? Tim, just for standardization or to sort of reference ourselves here, what did we do before we had large cloud-based collaboration? I remember a time when literally, you rolled up a rendering into a paper tube and you went down the office, you unrolled it on someone else's desk and said, "Look at this."
Yeah. I guess so. Manual collaboration, but between people walking between different departments, or using different applications and then transferring those via files, via email, etc. So we're moving into a world where we can remove some of those bottlenecks and the non-value added tasks of the typical engineer's day.
Yeah, Daniel, from your perspective, what Tim called the non-value added tasks, I think we thought as the frictional part of the process in getting a design looked at, getting it reviewed, perhaps getting it approved. Even a younger engineer designer soliciting input from a colleague that is more experienced, basically. Is that kind of thing, do we still expect that to go on now with cloud-based systems in the same way that it did before?
The cloud changed completely the way of designing things and to collaborate between people. Okay, you can connect yourself. You are in an airport. You connect yourself to the internet. You connect directly to the database of either your customer or your suppliers or your own database. You share data. You can easily copy or share 3D models that you can rotate, annotate. It's really a different way of working. It's really a revolution. You know, the French like the revolution. So it's a real revolution, which happened a couple of years ago, and which is now more and more even perceived as natural by the normal people. They use cloud for their pictures. They use cloud for their music. So it's really a super change. But the good news is that it just gives more time, as we are not doing those stupid stuff which are where we're wasting the time. We have more time to do the real work, invent, innovate, make new things. That's quite important for me.
Yeah. Kevin, we're going to get into sort of the deeper aspects of this technology in a moment, but it's at this point, we're talking a little bit about the human factors aspect of this. There was wide perception amongst the engineering community that I spoke with, and I talked to especially manufacturers worldwide, that there would be resistance to this kind of technology. Is that the physical shoulder-to-shoulder design review process of everyone clustered around a conference table with a blueprint rolled out, that couldn't be duplicated by using a technological solution down there. Now, that's clearly not the case, but what made this transition as easy as it was? Do you think it required a younger generation of designers and engineers, or did everyone just suddenly jump aboard?
I guess in many companies you'd find some people that haven't jumped aboard yet. Human nature, it's change, right? It's like anything. If we're used to doing things in a certain way and we hear about change, like, change is good, but I'm fine that you need to change. But certainly it's like anything. I think we're all fairly skeptical of when a new technology comes along and you have a sales guy coming in and go, "Oh, this is brilliant." You'll be like, hang on a second now, let me see how I get value out of this. And, Tim mentioned that you roll up the paper and walk down the road. that changed. The way we collaborate changed, and the other thing is it gives people time back, right? We all have busy family lives as well, so it's not something I think that happens overnight. But to be quite honest, Daniel mentioned it. It allows you to get value, but you got to perceive that value, and you got to see the value for yourself. Then you're kind of going, okay, this makes life better.
Yeah.
But I also think it's not, the technology is one thing, but it's the cultural change. And Daniel said about the younger generation coming through that are used to all this. They're used to the cloud aspects. They're used to every bit of information being instantly available. And that they're going to expect that when they go into business and go into the engineering world. So that's the aspect, and the technology is there, but the culture has to allow it to change as well.
Yeah,
I fully agree. You know, I'm not a young guy, but I'm still using PowerPoint 2016. Okay, but all the kids, they are used to change. You know, to update every day almost their apps, to be sure that they are using the very last version of the apps, which is not something so let's say usual for older people.
Yes, agreed. Tim, I understand you have a background that includes some Formula One work, Formula One teams. I think Formula One might be an interesting microcosm for what we're talking about. When I was a boy and a Formula One fan, if the Lotus 72 was the leading chassis, then everyone played catch up. But there might be a mid-season tweak of a design, but basically everyone resigned themselves to the fact that we'll have to improve for next season. Now we have a world now where it seems that there is no single specification for a new car. It seems that they can do extensive redesign almost from race to race, almost from circuit to circuit.
Yeah, it's constantly evolving. It's a constantly evolving car that they're developing and bring updates all the time, and the technology. And I guess we talked before about non-value added tasks. From what I've seen in Formula One, they kind of try and get rid of most of those anyway. So they're pretty good at removing some of the things that take up more time than is necessary, let's say, and streamlining their design processes. And they tend to bring all their design teams into a single place, in a single design office, and therefore they still collaborate quite from a human perspective, but they're using the technology as well, and they're good at breaking down those silos between different departments. But there's still room for improvement as well, because they also don't have a lot of time to look around and change, because everything's got to be developed for the next race or for the next season at the longest amount of time that they've got. So yeah, it's difficult to kind of look around and see what's out there and make those changes because they're moving so fast.
Yeah, Daniel, you're all about CATIA. CATIA, I think aerospace automatically. So it's if we think about the aviation industry in particular, that is a little bit like Formula One in the sense of it's not mass production in, say, the motor industry where you're looking at millions of units. It's perhaps dozens of units to hundreds of units for many of these aviation projects, but they're also very complex projects, and ones in which you're not changing the specification in the way a Formula One team is, but you're certainly iterating a design to optimize one through multiple steps.
The key big thing in aerospace is that every single part which is designed is validated by CAE simulation. Okay, every single part. So even in Formula One, they don't do that, but in aerospace, they do that. And the good news with cloud is that you can harvest collective intelligence. Every single actor of the process, the engineer, the me engineer that I am, the stress analyst, maybe even the operator on the assembly line, he can have his voice. He already had his voice in the past, but now we can listen to his voice, okay? And we can really converge to get the ultimate solution. It's really a question of we are breaking the silos. So the cloud is breaking the silo. It's very, very critical, okay? And aerospace is a little bit ahead of the rest of the industries regarding this topic.
It's funny you mentioned it. About roughly 5 kilometers from where I'm sitting right now, in 1957 and 58, a design team worked on a very advanced military jet, CF-105 Aero. And it was a very difficult project because aerodynamics was not fully understood for very high speed, high performance delta wing jets. And they developed a technique where the simulator, originally designed for pilot training, was fed into the design process, where the pilots who were learning before the prototype was built how to fly in the simulator would send feedback to the designers about things like control forces, for example. And that was fed into the design. It was a very early example of something that we now regard as a common part of the design process. So Kevin, that is sort of perhaps the earliest form I can think of a virtual reality kind of environment where you repurpose a flight training simulator and use that as a design tool to try and let the pilots feed something back to the designers. That makes sense in the aerospace industry because you're developing cockpit simulators at the same time you're developing the hardware. But we're looking at a world now where you might be able to translate that into civil engineering or automotive engineering or bridge building for that matter. What's the leap? What's it going to take to make that, do you think, the standard way that we design things? Put the goggles on.
So let me put it this way. It's happening in many industries already, not necessarily VR, right? But VR to me is a nice add-on, but the fundamental building block is that you have digitized your model, your design. You can simulate things. You know, in many industries today, talk about virtual commissioning. Before anybody builds a factory, a car or whatever, they put it through all sorts of simulators. So it's not just a nice, cool 3D design that a nice video cartoon thing that I have. I run physics engines on these things and physics simulations, as in metal brittleness and fluid flow and wind tunnel and backed up by decades of mechanical engineers, chemical engineers, the competencies that are in the industries. And Tim mentioned earlier, it's like a lot of this stuff is all about culture and we change it. It's also kind of changing the process. And what I mean by that is that the process, when we were walking around with our paper things, and that's going way back. A lot of people listening to this was like, I've never seen a paper design, right? We've always had digital because we've had CATIA or something for the last 20 years. But it was kind of serial because you had one master design and I had to take it to Tim's office and Tim scribbled on it. And then I had to take it to Daniel and whatever. So now it's in the cloud. I can have multiple people looking at multiple pieces of it. It's not serialized anymore. And then, as Daniel said, I can bring in all this collectiveness. Cut a long story short, I suppose, the advances in technology. I used to be with Intel. So look at the chips, and you have NVIDIA, and you have all the various pros with the chips. Look at the telecommunications. Look at the graphics capabilities. Look at the storage capabilities. Look at the cloud. Look, add all. It's kind of a perfect storm. You suddenly get to an environment where you can collaborate on designing something. I think you mentioned at the start, it was like, well, you design something, but then you have both dreaming and developing it and designing it. You can now do that in a immersive way. Now, immersive is a spectrum. It might be just simply that I have a photorealistic type 3D model of whatever I'm building, but I'm looking at it on a 2D screen, which is fine. And I can collaborate in that. We can draw on it and scribble on it and whatever. And we're all sitting at, let's say, our computers and our laptop screen. But somebody else could put on a VR headset and you have all sorts of plugins, and I can be in that environment. And whether it's AR or virtual reality or whatever, it's just a totally new way that we can collaborate on the exact same design processes we've been doing for years. It's just we've got new tools, new ways to do it faster, lower barrier to entry, and it allows us just be more immersed in this stuff.
Yeah.
On my point of view, something you forgot to mention. For me, the biggest benefit of VR is a scale. You are inside an environment, you 2 meters high, you have the scale. And in the front of a normal screen, you don't have the scale. And because of this very well perception of the scale, you can make the right decision in terms of design. You can go much faster to find the right solution to a problem. It's quite important. Huh? It's not a gadget.
If I may, it's spatial computing. I know of a company designing some offshore oil and gas things. They do it and whatever. They give one of the engineers, one of the guys out working on the thing, VR headset and let him walk around. And he's big man, and he's going that the gap there is too small. I can't go through that with a toolbox. And to your point, I might look at a design for 10 years and not cop that until it's built, and then that's too late. So a great point.
Yeah.
Exactly right. Yeah.
One example I had, which it's not specifically around virtual reality, but more the space that we've got, and again, it's a bit about the cultural change. Is when COVID kicked in, the company that we were working with, they did their design reviews in a meeting room. That meeting room held 30 people. Yeah, so the managers got the information from the engineers and took that to the meeting to make decisions. So it was second-hand information that was then being used to make those decisions. When COVID happened, they then did those design reviews in a cloud environment, and they invited 300 people. So the right people were in the room, were in the meeting. When they made the decision and the decision was wrong, they were able to say, hang on a minute, I don't agree with that, and get the real information across to the to make the decisions. So I think there's some boundaries that are physical boundaries that we have, like that size of that meeting room. And when we take away those physical boundaries, then we can start to bring the right people into the right places.
Well, Tim, you've mentioned something that I think around the edge of something that's vitally important in engineering, at least in my experience, and that's configuration control. It's, in fact, my first job in design office, before I knew anything, essentially, was literally to run around and make sure that everyone was working from the same drawing, the same revision. And there was a distribution sheet on the outside, and you'd run around with a clipboard and physically take away the previous version of that drawing, hand the correct one, and then they would sign off. So the chief engineer could make sure that when they had that telephone call, that everyone was working from the same drawing. And it seems like a ridiculously simple thing, but it's incredibly easy when there are 40 drawings in circulation to have one individual working from a D revision instead of the E revision. And then it creates chaos. It ripples through the entire system, which can be very difficult to find and to filter out. And when you're in a time-sensitive project, to lose a week, and you could easily lose a week, we discovered, from one single drawing in the wrong hands, basically, you create another layer of bureaucracy just to attempt to police configuration control, to make sure everybody's on the same time. It sounds like, Tim, what we're talking about here is a situation where that's just not even a factor anymore, because everyone in real time is always looking at one single source of truth.
Exactly, that's the term. That's the right term. The single source of the truth. You've got one item. You're not moving data around and creating copies of that data. The data lives in the platform. Everybody can reference the right version of it, and there's only one version, one single source of that particular version of the part. So multiple revisions, but you're still referring to that one single source of the truth. Yeah, and that's massively important.
It's super important, because especially for the manufacturing, if you are imagine you are manufacturing the B version and there is a C version actually in the engineering office. Wow.
Yes.
Bad things happen. But if I may, it's not just, to Tim's point, is like everybody can have one version of the truth, and that's the latest. And no, that doesn't get away with the sign off and the different phases of development. And there might be a couple of branches, for want of a better word, in terms of where we'll try something else with this bit and whatever. But and again, this is going way back, right? But it's like, as you say, I was trying to find the right piece of paper, and then it's like, well, what changed? Can I get the old piece of paper to look at it and kind of map it over? Now, digitally, I can go, well, what's changed? I get a revision history. I can see who changed it, why they changed it. It's all documented, right? Now, again, back to the process and whatever. And as Daniel says, well, we're manufacturing part B. Tim and myself are working on C, D, E, and F, because I know maybe we're changing component supplier, or we're changing something, and the guy supplying that piece, they're giving us a new design every 2 hours and whatever. It still needs to be managed. It's not organized chaos. But the digitalization, the tools, the cloud, the connectivity, again, that barrier to entry, that speed to get things done and simulate things and try things is we've never had that.
It's the visibility of that data. You can work off revision B. Revision B is the one that's released. Somebody's doing C and D, but they're not released. They're what if scenarios that they're working on. So as far as the company is concerned, revision B is the gospel. That's what you're making at that particular point in time, because that's released. So everybody can see that, but your design departments can innovate on revision C and D and look to the next iteration of that design.
Tim, in serial production in the automotive world that I come from, there's a tendency to hold back design improvements, to aggregate them and gather them. Mainly because it was impossible to incrementally improve a product because your drawings would go through the alphabet. You'd have so many revisions, there's no way you could police it. So there'd be a tendency for the senior engineering manager to tell a bright young engineer and say, that's a great idea, hold that thought, we'll implement it at the next design review for next year's production run. Yeah, or in some cases, 18 months out at that point. So really useful things got put in the back burner. And there was always a risk when a good idea was put in the back burner that it never happened. It sort of got shoved down a siding somewhere, and there's just no way to loop back and pick it up. So good ideas could disappear or be delayed for a long time, perhaps indefinitely. With this kind of cloud collaboration, it sounds like we can eliminate that, or at least reduce it dramatically.
Yeah, we can reduce it dramatically, I think. Yeah, and we can manage it, and we can apply configuration control to build those changes in at the appropriate time, but make them known by everybody, make them visible, and make them available to be adopted by manufacturing at the time that they're able to adopt those.
Yeah,
it might not be.
Something I would like also to add is that it was not impossible in the past. Let's imagine I am the OEM and I'm working on a particular product in assembly, and I have suppliers, and those suppliers are working on sub-assemblies. But I don't want those suppliers to see the complete assembly because I want to protect my IP, or maybe it's confidential. So thanks to our solution, you can now say this guy can only see this sub-product, this guy can only see this sub-product, but we can still have a collaboration, a review, and I will see my full assembly. I will tell them, hey guys, there is a problem here, and they will only see what they are allowed to see. So that's super cool.
Yeah, Dylan, I'm glad you brought that up, Daniel. That was a common issue in the automotive industry where industrial espionage was very real, and security is a real factor. We think of industrial espionage as a factor. There's also political espionage and intrigue going on. Many firms, of course, have military contracts, and a new evolving realm of so-called dual-use products. Things which are not themselves military secrets, but things which are nonetheless watched and monitored because they have potential application. And this has the potential for drastically increasing this complexity, this regulatory issue at this point. Is these cloud-based systems, is this something which is it going to be possible to get a grip on this so that you can monitor exactly who's watching what, so that if the government comes knocking, you can say, look, our flanges are not being used to build atom bombs in some third world country?
The security aspect, I mean, is obviously a massive thing. We're talking at the minute with sort of some of the large defence contractors around some of the big defence programs that are multinational, and how you can use the cloud technologies. I think technology is one thing, but data sovereignty, how that data has to live in certain countries and not breach borders and things like that. So there's a dichotomy of kind of how you make a collaborative environment that multiple countries, multiple organizations can all work in, but then still keep it sovereign, the data sovereignty and IP protection. And so there's a few conflicting things that are there that are beyond technology. So technology can answer some of them, but then when you put national borders in and things like that, and put the defence world in, then there's other sort of non-technical considerations that need to be put in place.
Right.
If I may just add to that, for folks that know me, I keep kind of going, technology is usually the easy bit. And granted, there are technology issues, and we talk about protecting the data, and I can encrypt everything, and I can have personal algorithms and two-way authenticate, blah, 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 blah. So the technology is there. And again, it's not that, we're trying how you use how you deploy the technology. You may have a private cloud. It might be on-prem. It might be not connected to any other network, but it's the same technology as you could use in the public cloud that's sitting in somebody else's data center. So to Tim's point, it's back down to the technology is there. How do you use it that in a way that makes sense and doesn't become too complex? But it's kind of back to the processes, and as good as the technology is today, and until quantum computing arrives in a couple of years and whatever, or 256 keys start to change or whatever, our weakest link in all of this, in cybersecurity, in espionage, is people, right? And in some ways, human nature hasn't changed in 4,000 years, and hopefully it probably won't, right? But it's the ability to be able to protect stuff is getting better, but at the same time, people doing off nefarious things hasn't changed either. So but it's not a technology problem. It's more of a people process and geopolitics. Look what's going on today in today's world, right? It makes it a bit more complicated.
Yeah. Daniel, we're talking about a virtual reality world where you're going to walk through the fuselage of that airliner before anyone has even made a prototype at this point. So are we looking at a world in which you may have a system that restricts what you can see in that virtual world based on the thing that you're interested in? So if you're involved in APU installation at the rear of the airplane, you can walk through the fuselage virtually, but perhaps you won't be allowed to peek into the engine cowlings. Is that how we're going to control this?
Yeah, it's already there. You can already do that, so it's not a problem. We can filter out what can be seen by the different actors of the review to just what they are allowed to see. Yeah, this is already possible. So, but my dream is to go, and we start to do that, is to go further. Review even in 3D, whatever in VR is nice. What is also nice could be to remember we have the scale. We know the scale to do design, in an immersive world, to modify, to change the position of this pipe, to modify the screw and to change it by a smaller one, because otherwise my hand cannot unscrew this guy. So this is also something we should work. We are just at the beginning of that, but I'm sure this will be a very, very big step to go further and to make less errors and to design right the very, very first time.
Mm-hmm. Yeah, no, I don't know.
We shouldn't also forget about augmented reality. So being able to overlay the virtual model onto the physical parts. So that's already in use for being able to look at work instructions on the shop floor and be able to identify which brackets have been put in place to route electrical cabling, and then overlay that, and also check the quality of the parts that have been put in place using augmented reality, overlaying the kind of the virtual model, the virtual world with the onto the physical world.
Mm-hmm. Could I make one comment on that as well, if I may? Because some people will say, or listen to us, will go, but we've had AR for years, and some people have been dabbling with VR for 10 years, and we've had digital twins for 20 years, blah, blah, blah. So what's new? And certainly what I see in many industries, oil and gas, industrial, whatever, was that you typically create a VR experience in a snapshot in time. Here's what the thing looked like today, and it took you 3 or 4 months to get it all working, and then you took it out. And the same with AR, and then someone changed something, and the real world looks different now. Where this stuff comes together is Tim mentioned one version of the truth, and I get to see the version of the truth I'm allowed to look at. It's the production B signed one. Maybe I'm working on version D, and I'm working on this bit. But when I put on the VR glasses, because I'm pulling it in almost real time from the master of version B, version C, version D, I only get to see the bits I'm allowed because we have single sign-on and that changes the game, because I can see what the latest design looks like right now. I don't need 3 months for someone to build a monolithic app, and then when it changes, I have to start again. That's where the paradigm shift is coming from my perspective, that kind of real-time digital twin, one version of the truth. Yeah, and that's what the cloud enables.
Exactly. It's the living virtual twin of the assembly, or and also the environment that you're working within as well. And it's feeding back the real information into that virtual twin so that that can be updated with the data that's coming from the shop floor or from the maintenance of that aircraft, and being able to have that as a living, breathing virtual version of the physical product.
Yeah.
Knowing that now the new technology of you are able now to digitize the complete plant, the complete interior of a plane with color coded. It's very cheap. It does not take that much time. Maybe an half a day you can do that, and then you can combine your CAD model within the legacy context. The super high value to make the right decision. Oh, I designed this one, but you will never fit this particular place, which is a legacy place. And now it's very common. Huh? It's not something in the past. It was expensive. It was taking time to just digitize. Now it's very simple to do. And this also will bring a lot of value. And CATIA allowed to do that. Combine the virtual world designed from CAD system and the real world, which has been digitized, color points cloud, which is very helpful to understand the environment you are working in.
Now, at a recent trade show, I sampled a training device made by a manufacturer of welding equipment for heavy structural welding. And it basically it was a virtual reality system, goggles essentially, and you picked up a TIG welding torch and it had very much everything but the smell of actually welding. It was remarkably it's remarkably realistic. And as you sort of stand in the bridge and look around at the girders basically and reach up and, make a bead, put it together. And then the thought occurred to me sometime later. I thought, wow, is this something you could integrate into the actual engineering design process? Where we're designing the bridge girder structure at this point there, but is it, perhaps you design it to produce a desired outcome, but is it also something where you could virtually bring in the people that assemble it and simulate the actual assembly process or the process of, I know the aviation world does this in a sense of, if you're going to rivet something, for example, or bond something together, there's a fit check process. But in the future, could we be looking at a world now where you're simulating everything? You're simulating the design of the aircraft wing, you're also simulating the man who fuels it and the individual that opens the inspection port and climbs inside. Is this a future you think of broad scale application? Daniel?
Yeah, we can do that today for manufacturing.
Yeah.
We can do that today. We can even, why not, with VR, we can even see, let's imagine the particles of a fluid in a CFD analysis in 3D. So you can see how the flow of the air will move around the car body. So it's very, very impressive what the technology. So yes, you can do that today.
So for me, it's all about simulating it virtually before you've spent any real money on making it physically. So when you make it physically, you know what that it's going to work. You've tested it. You might have to physically test it again, but you're expecting that to pass because you know the outcome, and eventually we'll kind of remove some of those physical tests as well because you've been able to simulate everything within the virtual environment, and it's having that it's to do that is relatively inexpensive when you compare to making mistakes of cutting metal and using worldwide resources to make things and getting it wrong. So it's all about trying to do that upfront simulation to make your mistakes because we make mistakes. We're human, but you make them in the computer and it doesn't cost the world anything.
If I may, that's a key point in all of this because the buzzword I often hear is design many times, build once. And to Daniel's point as well, and Tim is making there is that, okay, I can design, I can simulate. And again, it's not just like a cartoon computer game. It's physics simulations based on years of engineering, material science competence. And Daniel mentioned earlier is that in the airline industry, it's like, okay, well, I changed this little bit over here, but I need to validate in the entire plan because these are complex systems, right? It's not just, sure, I'll take Kevin's word for it. It looks good. And I can do all that. Can you imagine the sustainability benefits from this? Now, granted, we have more computers, we have more data centers, they need energy and whatever, so everything has a carbon footprint. But the cost of getting the metal, cutting it out, cutting the wrong design, start again, the sustainability angle, and what you're seeing in many industries as people are designing and iterating and whatever, they're designing it in a way, can I design it better so I can recycle it easier? Because I think someone mentioned there was breaking down the silos. The guys who recycle stuff are normally not involved in the design of something. And they'll be going, oh God, why did you bolt that on there or glue that on there? That makes our life so much harder. Can you design it in such a way that they're involved in breaking down those barriers and stuff? And that's where this collaboration with people that were never involved in the process before because it was too complicated. That's where we're headed. And this is transformational, in my opinion.
And I guess typically all these things have happened, but they've all happened separately in separate applications without the data being joined up. And we had a discussion with one of the Formula One teams about an analogy of the aerodynamics of the Formula One car. If you put a big lump in it, then that will disrupt the flow. Yeah, so they won't do that. It's the same from a data flow perspective. If you have to go out and take that data out to something else, then you've broken the flow. Yeah, that might be a copy of that data, and that then takes time to resolve, takes energy, and also can lead to making mistakes. So it's trying to keep that data flow as seamlessly as possible.
Well, Kevin, you've injected environmental. I'm sorry. Go ahead, Daniel.
Sorry. No. I just said that the numerical continuity is extremely important. You cannot imagine, instead of being forced to change data with files from one system to another, if you can allow to have a full digital thread, the benefits are super huge.
Yeah.
Sorry, Tim.
No. Okay. Kevin, you've injected the environmentalism into the conversation, which I want to come back to because there's no way to not talk about it. It's the elephant in the room here.
It's business resiliency is the word to use, right? Because you need to be able to deal with supply chain changes, cost of energy, cost of raw materials, substituting things. So absolutely, the net is a environmental benefit. But today it's all about business resiliency. That saves money.
Tim, it's one of the major German automakers who shall remain nameless, although they're based in Bavaria and very famous. To comply with a German environmental law, they're required to sort of account for the car at the end of its life. And they have a disassembly line where they literally take the vehicle back from the owner and they take it apart and they have to recycle things like resins, plastics inside. Historically, the automotive industry, one of the great things an engineer could fall back on was if he had a stress strain problem, is specify a different grade of resin. Maybe go to an engineering resin, maybe go to a copolymer or an alloy, and you could sort of cheat your way out of a problem by tweaking the moduli and the property of the materials you use. Now we're talking about a world in which you may be restricted to 6 or 7 different basic commodity grades of resin because you can't recycle 50 or 60 different types of resin, especially highly filled ones. So this is a tremendous additional pressure on a designer to account for every gram of material, and everything has got to work in the design and literally carry its weight and pull its load. How much do you think this cloud collaboration plays into that increasing complexity?
Yeah, absolutely. I mean, the tools are there now to allow the designer to check the environmental impact of his design and check based on specific rules and specific databases of information. And so as he's doing his design, he can check whether that meets the environmental impact, whether that meets the cost impact, whether that meets the weight impact. So the tools are all there to enable that to be part of the general design process of the designer. So typically before, the designer does his job and then the weights guy looks at it and then the cost somebody from purchasing looks at it, and everybody has a different viewpoint on that, but that all takes time. And now the designer can get that upfront view and go, actually my design doesn't meet this environmental impact, so I need to think again before it's gone out to other departments and other people.
Yeah. Now, we haven't talked about the cost aspect of this, but of course, they're inextricably linked about this. And Daniel, I'll throw this one at you. Sometimes in the design process, wow, it's not working the way I planned. I need to add one more fastener, one additional screw. Or, boy, I may have to add a bit of sealant, perhaps, here to contain. Suddenly now that has an incremental cost implication, of course. And of course, the old way we did this is that you revised the bill of materials, you ran the numbers through, and somebody in the accounting department from purchasing said, okay, that's going to add 8% to the cost of your assembly. And then the chief engineer would scream, no way. You're already over budget on this part. Go back and find another way. And so you would sometimes design solutions are not necessarily optimized mechanically, but they're optimized from a cost perspective. Can we integrate that notion of cost and the shift in the bill of materials with this collaborative process the same way and speed that up too?
Absolutely. It's what we call design to cost. In design, when we are designing for manufacturing, you cannot design something which cannot be manufactured, obviously, but you need to manage the cost. The cost is very important. It's the primary constraints. So, and yes, in such solution, our solution, for example, we are not the only one. We integrate this factor. It's very, very important, and it's mainly due to we are in the database. We can have we can add information to every single part from a cost perspective, and then we can challenge which one is the best, and maybe change or ask the designer to change his mind. Hey guys, it's no longer, as you said, no longer fastener because they're too expensive, because maybe the supplier is no longer existing. There are no longer rivets, and you will have to add glue. And this is very easily done with a solution to switch a fastening process to change the boom. And so every single designer, a mechanical designer, has cost in mind since the very beginning.
Yeah.
and the tool allow him to guide and warn him, hey guy, you are over the budget, so please change something, like we do for the weight, for example.
Yes,
and it's also having access from a design point of view to designs that have happened previously as well. And so it might be that actually doing an innovative design is fantastic, but the cost of it is impossible. So actually having at the designer's fingers all the previous designs of that bracket or that fastener or whatever, that he can then go and that one's approved by purchasing because it comes from a preferred supplier list and things like that. Having all that information ready to hand as he's doing the design process or as they're doing the design process is a critical thing. And previously it wasn't to hand. Yeah, now it can be. Now it can be part on the guy's desk within the tool set every day.
Yeah.
If I may, Tim mentioned that earlier. It's about breaking down the silos. And Tim, as you said, there was always purchasing guys and accountants and whatever. And then they'd get the new bill of materials and they'd get out their calculator or spreadsheet from hell and they'd start hit and return. Because the systems are linked. And it's not trivial, right? There's a lot of hardcore engineering and competence gone in to make all these things work. But I can now go, well, if I take this part and put it in, hit return, cost. And it's not just potentially the bill of materials cost, but I can now start factoring the cost in the life cycle. What's it going to cost me to recycle this thing?
Yeah.
And I might need to put more money in up front to stop money leaking out somewhere else. So could we have done this years ago? Yes. You'd have about 10,000 people in a massive room for 6 months arguing about something. Now you can do it in ways that we just could only dream about, maybe even 5 years ago.
Yeah. And we haven't mentioned quality. And as an old manufacturing guy myself, I've got to bring that up because it was always a factor. When an engineer designed things, sometimes we could always tell the seniority or the experience of an engineer by the tolerances they specify in a drawing. It's the ability to actually hold a tolerance is a real issue in manufacturing. And there are times when the back and forth in part of the design process used to be the manufacturing engineer talk to the design engineer and saying, look, do you really need to hold a tolerance of 1/10 of a millimeter in the diameter of this hole? It's just not that important. For a bearing race, it's critical. for an inspection hole, it's only important that the hole be there. And so there's that sort of back and forth going on. Is there a role for simulation and for these sort of advanced technologies in here to sort of semi-automate some of those processes? Because we're with statistical process control now, it's not trivial anymore. It's no longer a bloke with a clipboard and a micrometer at the at the loading dock checking these things. Daniel, what do you think? Do you think there's a future where we can automate that too?
I think I already mentioned the buzzword design for manufacturing.
Yeah.
Depending what manufacturing process you actually selected to produce your part, which the system should help the designer to know what are the constraints coming from this particular process. If it's a sheet metal part, it's not the same constraints. You have maybe more freedom than if it's a mill part, if it's a forging part, if it's a casting part, if it's an additive manufacturing manufactured part, you have maybe. So it's very important, and we take a particular attention to help the designer to do a design which is doable at a good cost, because as you said, and you are perfectly right, if you put a tight tolerance, it will be very costly to just actually mill this guy. So, and this is very important. And design for manufacturing for us is super important. And the ability to select maybe propose, maybe through AI, what is the best manufacturing process for a particular part or a particular cost is also something which could be helpful for the designer.
Daniel, you
beginning of the story.
Daniel, you did not.
He said AI.
Yeah, and Daniel, and hold that thought, Kevin, about AI, because we're going to go there for sure. And Daniel, you've dragged the conversation into additive manufacturing, which we knew we had to go in that direction at some point. Tim, you're connected to the F1 world, and if ever there was an industry, I think, which has embraced additive manufacturing, it's got to be F1 at this point. I mean, there's less and less metal in the cars at all now. The things seem to be, composites entirely.
Yeah, I mean they're hugely composite structures, and then additive parts are used in various different places. So yeah, it's definitely an area that they're very, very interested in and are using today, and using some of our technology. And again, the flow of data. We're one example with one of the teams where they did the process of defining an additive part, but it took sort of 5 different bits of software, and they took it from I think it was 17 hours of the design activity through those different experts, and within the collaborative environment, then we could take that down to a single hour. So they're able to do that 17 times. So the quality gets better, the performance gets better, or they can do it quicker. So it's definitely that integrated environment where you're not passing data as files backwards and forwards. You're able to give the tools to the designers so that they can really do their iterative design and create an additive part or a traditional machine part very, very quickly, and save weight, save cost, improve performance.
Yeah. Now, we've talked about one thing about additive manufacturing is it allows you to produce parts which are very odd from conventional engineering sensibility. I've seen components which look like the branches of a tree, or they look like sort of the bone of a whale. And historically, we teach engineering in Cartesian kind of rectilinear ways. We think about forces, for example, as they're resolved into right angles primarily. So it's a triangle of forces always. And we see every Warren Truss and every bridge we've ever seen. We know it's designed that way for a reason, because not because it has to be, because that's how we can visualize how the forces flow through the structure. FEA basically took that kind of Cartesian rectilinear thinking and resolved it down to tiny, tiny little volumes and then stacked them all together. But we still think in those terms. Now we're looking at a world where if you're 3D printing structures which don't even look like structures anymore, they look like organic shapes at this point, engineers are expected to somehow imagine structures which are unimaginable. So is this where this software has to jump in basically and say, I see that bracket, but you know what? No, we're gonna let the AI iterate that into something you can't even imagine. Is that the future?
It is, but you still have, if you are a mechanical designer for 40 years, like I am, I I don't have. I have to open my mind. Okay. So and it's very difficult to get rid of 40 years of mechanical, experience. So we have to change. So we have to teach every single designer what this type of technology can help them to achieve in terms of shape, in terms of function, in terms of specification. And it's, by the way, a lot of big companies in every country, every industry, they are doing that. They are teaching what are the benefits and the constraints, because there are also some constraints of additive manufacturing. But the idea is really to open the mind. And the young guys, we're also talking about 4D printing, not 3D printing, 4D printing. When you print a part and automatically the part is, for example, making a different type of shape. And this has to be trained. So it's also a question of training people about what the technology can achieve. And then it will open their mind. So
yeah, Kevin, Kevin, as a young designer, I would show a 3-view rendering, perhaps an orthographic projection. Very frequently, the senior engineer, and I regarded him as an ancient man. My goodness, he must have been 50. And he would say, build it. I'd go down to the machine shop basically and have a tool and die maker make a wooden mock-up or something out of a commodity aluminum or something and put it on his desk so he could pick it up and then and hold it and rotate it. We're talking about 3D printed structures now, which are I want to say literally unimaginable. Not something you could sort of visualize and render at this point. Is the AR, VR world going to be the only way in which we're going to be able to even understand what we're designing when we're looking at shapes this complex? Are we going to have to put the goggles on to sell it upstairs?
Maybe to visualize it before we print it or something. But in order to sell it, I'll still need to verify that it's structurally sound. And it might look nice, but whatever I'm using it for, is it going to fit the purpose, right? Is it safe, reliable? It's going to break in 6 months or whatever. That's where, so again, the way I'll do that, the old way is, well, we'll make it and we'll put it out and in 5 years we'll figure out whether it works or not. Now you simulate. And again, I find it fascinating when you look at the capabilities out there for whether it's fluid dynamics or molecular integrity or brittleness or, pick a material science discipline. There's software that will simulate that. And then whether it's different stresses or wind or environmental factors, what happens if water, or a big thing right now is always we're going hydrogen. Can I put hydrogen into this pipe? Well, you can now simulate based on the molecule interacting with whatever other molecules are in there. VR, AR will help us maybe visualize something, but we're not losing. This isn't about kind of cartoon graphics and 3D printer in the backyard and we'll all build stuff. The rigor, the design integrity, the quality, the reliability, they're not going away, but it's the tools that we use to get there. And in some cases, it may be that, it's not a take our word for it, but you get to a decision where I trust this by using the software and the tools that are there today, as opposed to, well, you build it, let's put it in the test rig for 6 months and then come back to me and tell me how it worked. That day is changing. But you still need to trust the stuff, right? That's the cultural change, the mindset. That's human change. That's hard.
Yeah. Tim, I was thinking about safety briefly about this. In the I know in Formula One now they crash test monocoques to determine G loading in case of accident for the drivers. In the mass production automotive world, of course, crash testing is a fundamental part of the certification of a design. We're talking about a world in which it's possible to iterate almost infinitely and make continuous running changes in the product almost on the assembly line, because of the flexibility of the tools we're talking about at this point. However, at some point then, you deviate the design away from that which has been certified. So the certification process almost locks you into not changing something until you can build another one and then crash it into a block wall. But now we have simulations that actually allow us to actually even simulate the crash testing or the crash at this point. So is it for safety critical industries, aerospace, automotive come to mind immediately. There's some marine applications as well, civil engineering at this point. Are we going to reach a point, do you think, where we can turn to the regulatory bodies and essentially say, we don't need to crash 10 cars into the brick wall with high-speed cameras here? Here's the simulation. We've validated it. We're ready to go. Approve it.
Yeah, well, I think yes, we will. How quickly we'll get there, I'm not quite sure. But yeah, it is again, it comes down to cultural change and acceptance of the simulations. If there'll be a period of time where we've got the simulations, but we've got to do the physical test to tick it in the box to say that equals that, and then there'll be a period of time where we go, right, okay, we don't actually need to do that £1 million test to blow up that engine or whatever it might be, because it's we've got the simulation of it, and therefore we trust that is the correct results that we're getting. So
yeah.
So I think at the minute the technology's there to do that simulation of the test, but there's still a need to validate that test and with a physical test. But yeah, over time that trust will be there. That and those expensive physical tests will be sort of fewer and fewer, I would say. But yeah, it's gonna take time. There's we're working with one of the large aerospace companies at the minute, and to do sort of smarter testing, so make sure it's a better testing process.
Daniel, it's 120 years ago. If you were a young man interested, in those days it was all men, interested in aviation, you might be a Louis Blériot or a Farman or a Santos Dumont or one of these early pioneers. You just picked up your spanner and you built something in a shed, and then climbed inside, and then you flew off. And if you lived, you could become a great hero and a pioneer. And if you didn't, we all learned from the mistakes. We see a new renaissance now in aerospace of small firms that are developing radical designs, things like air taxis, vertical takeoff and landing, advanced electric propulsion systems, business aircraft, even fairly medium-sized cargo and commuter-sized aircraft, out of individuals where it's 3 or 4 brilliant young people working, out of a garage. This is not possible using conventional design techniques. How much is this cloud collaborative kind of systems we're talking about? Are we looking at a revolution going back to the sort of those pioneer days where 3 people with a good idea can go and design an aircraft? I mean, are we facilitating a new way of doing engineering?
Yes, for sure. Why? It's very simple. They are doing super complex products. Okay, those super light, plane, whatever, are super complex. Super complexity means a lot of different complex simulation software that they have to use. The cloud brings a very, very small benefit, but it's super huge. You don't have to take care about the IT infrastructure. You connect yourself to the cloud, and you can use those complex simulation software and complex design software to build everything you dream of without taking care of, I have to do a backup of my data. If my laptop is breaking, I lost my data. No IT infrastructure. You can work everywhere, from every place, at any time, on every device, even a smartphone. You can run CATIA on a smartphone. Okay, so and this brings for them a lot of they have time to just innovate, not take care of IT stuff. That's my view.
Yeah.
A couple of years ago, you had to go off and build your data center first before you could do some of this stuff. To Daniel's point, it's like, well, if you want server capacity, well, you just pay for what you use, and away you go, right? The barrier to entry and the ability for people to try out new things, the technology just enables people to go do this. Whereas years ago, you spent billions to get there.
Yeah, it's very, and for those startups, it's very scalable. They can start small. They can think big, but start small by adding just maybe structural analysis. And now they do composite parts. They can add the composite stuff and make composite analysis. And then maybe the 3D printing and so on and so on. They can really grow depending on, by the way, they can change their mind. Maybe composite, they forget. Now they just focus on aluminum. I don't know. And this is very possible on the cloud. The cloud is very scalable, very flexible.
Yeah, incredible.
You're not tied in. You're not tied into a 12 or 3 year software contract for millions, right? It's dollars per seat per month.
And they're making decisions based on their CEO, who's deciding that actually we're going to subcontract all that. So yeah, we can kind of go, all right, well, that bit is out to the supply chain, and we can integrate the supply chain into that same environment as well. So yeah, that's it's very, very, very flexible for
incredible. John, there is so much to talk about. We could talk for hours about any of the individual topics we touched on here, and I hope we'll have a chance to do that again in the future. The clock must intrude. May I ask, in conclusion, on a 60,000 foot level, if you will, the 20,000 meter level, how about that? We're talking about a technology here which is democratizing the engineering process. We're talking about tools and techniques here that allow people that are perhaps not degreed engineers to do many of the functions that historically required someone who is a very, very skilled engineer to do, basically. Is this cloud-based, highly collaborative technology going to democratize engineering to the point that we broaden the field of design to people who historically would never have the ability to do so in the past? Is that where we're going in the future? Kevin, can I start with you?
Simple answer, yes, but that doesn't mean that we don't need brilliant engineers, because someone has to design or come up with something first, whatever. You can democratize. You don't have to become a master at CATIA to be able to use it as a business person to go, well, what if we do this and just let me dabble, let the engineers then, whatever. The complexity has not gone away. We need brilliant engineers. But if you look at the kids coming out, or kids, grandkids, whatever, they're off playing computer games. They're getting spatial awareness. They're probably learning how physics models things work, even though they don't in Minecraft when things bang off each other and whatever. They don't know what it is, but they're going whatever. They're designing things. They're the new Lego, the new Meccano is on a computer. When they come into the workforce in the next couple of years, they will demand the same type of tools. Daniel, you mentioned earlier, the music's in the cloud, our photos in the cloud. They just, that's just normal. So it democratizes things, but the core engineers, there's always going to be a role for clever engineers.
Tim, Formula One, a classic example. It was originally there were almost no engineers to be found in the paddock at all. These things were designed with a piece of chalk on the garage wall, and then the engineers have taken over completely. Is this democratizing going to affect other industries?
So I completely agree with what Kevin just said. You still need the clever people to do the clever, innovative work, and it's about how that data is now accessible to everybody else. Yeah. So typically they did that in their engineering software and then wrote a report about it, and that got passed around to everybody else. Yeah. Now the models that they produce are available to be used by everybody else, to be understood, to be consumed by people like purchasing and other departments, which typically went and bothered the engineer for information, and he or she spent a good deal of their time providing information to other people. Yeah, so that it's the democratization of the data out to the rest of the business, so that they don't have to spend their time giving that data out. It's already there.
Daniel?
Yeah, my view is that normal people in the future will do much more complex things than what they are doing today. Okay, normal people. And the super people, the stress analyst, the super expert engineer, they will do incredible things. Okay, so we will just improve, and the people will be more happy, because when you are doing complex stuff, and if you manage to do it, you are proud of you, right? So I think we will increase the happiness of the people, and they will do much more complex things, and because the product will be more and more complex. System engineering, software, electronics, mechanical will always stay there. But so that's it's why I foresee a very brilliant future for the engineering.
Wonderful.
Hopefully, I will see it for a long, long time.
Wonderful. An engineering future where we engineer happiness. Kevin O'Donovan, Tim Greenwood, Daniel Pizak, thank you all for joining me on the roundtable.
Thank you. Bye-bye.
And thank you for watching. See you next time.